All right, guys, I think it's working now. So I wanted to quickly go over the homework. So the first one was this satellite question. And you notice that they give us the mass of the satellite here and its radius. And they tell us that it's a cylinder. So the first thing that I'm going to do is I'm going to find its moment of inertia based on that information. For a solid cylinder, I equals 1/2 mr squared. So I'm going to do 1/2. The mass is 2,600 kilograms. And the radius is 3 meters. And we're going to square that. Okay, so if we do that, 0.5 times 2,600 times 3 squared, I'm getting 11,700. So that's what we get for I. And it's kilogram meters squared. Okay. We also know that it goes from rest up to 30 RPM in 5 minutes. Okay. So we can use that information to find its angular acceleration. So 30 RPM, if we multiply by 2 pi and divide by 60, we're going to get pi. So it's 3.14 radians per second. That's really sloppy, sorry. Okay, and 5 minutes is 300 seconds. So we can use that to find the angular acceleration. So I have 3.14 radians per second minus 0 over the time of 300 seconds. That gives me 3.14 divided by 300, 0.0104. So 0.01, we can say. 0.01, and that's going to be radians per second squared. Okay, so we have I, we have alpha, we can find the net torque. So let's do that next. Net torque is going to be I times alpha. We already have I, 11,700. We have alpha, 0.01. Multiply those together, you're going to get 117 Newton meters. Now you got to think about, where does that torque come from? It comes from each of these rockets applying a force. So if we go back up here, I'm going to change pens too. Let's just go here. Okay, so each of these 4 rockets is exerting a force. So for example, this rocket is pushing in this direction on the satellite, and each of the rockets does something similar. So the net torque is the result of 4 forces being exerted 3 meters from the axis and being exerted tangent to the surface of the rocket, or of the cylinder. So if you think about it, if we draw a line from here and we connect it with where that force is being applied, the angle between this force and this distance, or this position vector, I should say, is 90 degrees. So I can say that this 117 Newton meters is the result of 4 forces being exerted 3 meters away at an angle of 90 degrees. And I can use that to solve for F. And we get .75 newtons. So there we go for that example. Okay, next. In this one, it asks for the moment of inertia of the rotor and then compute the torque required to bring it from rest to 5 reps per second in 8 seconds. Well, you should already have the moment of inertia of this thing because we did it a couple of days ago. That came out to be 2250 kilogram meters squared. If you don't remember, go back and take a look at how we ascertained that answer. Now, to get alpha, I'm going to do the angular velocity at the end minus 0, because it starts from rest, over the time. Okay, so 5 revolutions per second, that's going to be 10 pi radians per second. All right, so 10 pi is 31.4 roughly. So we have 31.4 radians per second minus 0 divided by the time of 8 seconds. And that gives us 3.925. All right, so that's our angular acceleration. So the net torque is going to be I times alpha. So that's going to be 2250 times the angular acceleration, which was 3.925. And I get about 8,800 Newton meters. Okay, so if you have any questions on either of those two problems, let me know in the comments so I can go back and take a look at what you did. All right, now we need to start talking about a new concept, and that concept is angular momentum. So I want to bring this first slide up here and just recognize, going way, way back to the beginning, that anything that's moving is going to have linear momentum. Mass times velocity, the quantity of motion. We talked about that way back in September into October. But what I want to impress upon you at this point is that it's possible that an object that's moving can also have angular momentum, depending on what we call the axis or the origin. All right, so when we look at angular momentum as a quantity, we want to think about, all right, well, it's related to linear momentum, but it's going to depend on where you calculate it relative to. There's always a spot that you're going to calculate it relative to. All right, so I have a little bit more notes here on this. Okay, so it says the instantaneous angular momentum, we're going to use the symbol L, of a particle relative to the origin is defined as the cross product of the particle's instantaneous position vector and its instantaneous linear momentum. Okay, now we haven't really talked about what a cross product is, but let me just say this much for now. A cross product is a mathematical operation that you can do with two vectors to get a third vector. Torque is the first example of something that is a cross product that we've studied in physics so far. So when we look at how do we calculate torque? Well, we take how much force, we take how far away is that force being exerted from the axis, we find the angle between them, and then we do force times distance from axis times sine of the angle between them. Well, momentum, angular momentum, that is calculated in a similar way. You can see down at the bottom here how it's written out. So we can say that it's how far away the object is from the axis at that instant times its momentum, p, at that instant. Remember, p is mass times velocity, times the sine of the angle between them. Now, one of the biggest things I want you to recognize here, and I'm going to write this over here. So this is what they're saying. L is equal to RP sine of the angle between them. Okay. Now, we can break down P and say that's equal to MV. So we could say R MV sine of the angle. And really, When we do that, it's the angle between the velocity and the position vector to get the angular momentum vector. Okay. Just for time's sake, guys, I want you to understand that angular momentum is definitely a very kind of abstract concept. The quantity of motion of something that's moving relative to some origin, and trying to understand what that means physically is not the easiest thing to do, but it has a lot of very concrete applications that we're going to get into, later on. Let me just start by saying this. Imagine this scenario. So imagine you have a skater, an ice skater, who is skating on the ice in a straight line. So let's say they're skating in this direction. Okay. Now I want you to imagine for a second that they're skating on ice at the North Pole. This is ridiculous. All right. And imagine that the North Pole is an actual pole, like a physical pole, like you see in like cartoons and stuff. Okay. So this skater is skating forward and there's this pole sticking up out of the ice. I want you to imagine for a second what would happen if the skater is skating along and then all of a sudden grabs onto that pole as they're in motion. I think you can imagine that if you're moving in a straight line and then all of a sudden you grab onto an object and hold on, you're going to start rotating around that object. So this person who was skating actually had what we call angular momentum about that axis at that pole. Okay, so this is kind of the idea that we're getting into. All right, a little bit more about it. So the units for angular momentum are kilogram meters squared per second. Right? Both the amount of angular momentum and the direction of the angular momentum depend on where you choose the origin to be. Okay, it's all relative to an origin. We already talked about what this is, how to calculate it. And I wouldn't worry about this right now. The direction of the angular momentum is perpendicular to the plane formed by R and P. This is something that if you take another AP course, you take Physics C, or if you take a calculus-based physics in college, you're going to talk more about the direction of the angular momentum. Basically, the direction of the angular momentum is going to be along the axis of rotation. All right, but I'm not going to get into it in more detail than that for now. If we had more time in class, I would talk more about it, but for now, not really something to worry about. Okay, so let's use this simple example to start out. I want you to imagine that you have some particle, its mass is m, and it's moving in a circle, uniform circular motion. Okay, and we want to know what's its angular momentum about the point in the center of the circle. So let's say this is where we want to calculate the angular momentum relative to. Okay, so our angular momentum equation tells us you need the distance from the axis times the momentum of the particle times the sine of the angle between those two things. We'll take a look at the picture and you'll see why this makes sense. If I draw a line from the origin to where the object is at this instant, it makes this vector r here. So that is the radius of the circle. If I draw a line to describe the direction that the object is moving at that instant, remember, if something's moving in a circle, its velocity is tangent to the circle. So that's this. So here's my velocity vector. And think about it. If the velocity is in this direction, so is the momentum. It's in the same direction. All right. So the angle between this vector and this vector happens to be 90 degrees. So if I wanted to calculate the angular momentum of this particle, I would take its mass, I would multiply that by its velocity, whatever that is, and times the distance it is from the axis, the radius of the circle. Sine of that 90 degrees is 1, and we get this. So anytime something's moving in uniform circular motion, if we want to know the angular momentum of a single particle moving in a circle, we can get that from this. Okay. Now, I want to look at a little bit more complicated example here, and this kind of thing does show up every once in a while on AP. So Take a look at this one. It says, and this is actually from an AP test, a particle of mass m moves with a constant speed v along the dashed line y equals a. So you see it here. When the x-coordinate of the particle is x naught, that's here, the magnitude of the angular momentum of the particle with respect to the origin of the system is, and they give us choices. Okay, so there's an easy way to do this question, and there's a more difficult way to do this question. I'm going to go through the easy way because it's the way I want you to really start to think about it. So here's our origin, okay? What I want you to do is what it says here. Think about perpendicular distance from the axis times linear momentum. Here's what I'm getting at here, guys. The equation for angular momentum says this. R mv sine of the angle. Okay? Now, this is all multiplication. So you could say mathematically that that's the same thing as something like this. Hopefully you see that. Here's what I'm getting at. Yes, mathematically these are the same thing, but the way to think about solving it, if you think about it conceptually this way, this is going to be way more useful than thinking about it this way. Okay, let me show you. All right, so this r sine theta, r sine phi rather, represents the perpendicular distance from the axis. If you remember when we did torque, we talked about the lever arm distance, okay? That's basically what this is too, all right? So let's call it the perpendicular distance. Look at the picture. Here's the line that the thing is moving along, okay? Here's what I want you to imagine. Draw a line that intersects that line, that dotted line, that goes through the origin and makes a 90-degree angle with this dotted line. Well, the only way to do that would be this. Start here and go, ooh, I can't draw a straight line with this tablet, but imagine a straight line like this. Okay, so that makes a 90-degree angle with the dotted line. Think about how far that is. Well, you know, because you have the coordinates here. This is A. This distance is A. Okay, so now we know that this is A. It has a mass of m and a speed of v. Well, m times v times a. That's it. I'm done. This is the correct answer. Okay, now you can prove that this is true doing it the long way, doing it this way. You'll draw a line from here all the way over there. It's going to make a diagonal. You could figure out the length of the diagonal using Pythagorean theorem. And then you can multiply that by the m times v. But the angle between that diagonal and this v is not 90. It's going to be a different angle. You'll have to find the sine of that angle. I'll give you a clue here. When you multiply the length of that diagonal by the sine of the angle between it and this, you're just going to get a. And the whole Pythagorean theorem part with square root of x squared plus a squared is going to go away, and you're going to end up with this anyway. So if you start thinking about angular momentum in much the same way that you thought about torque, what's the perpendicular distance from the axis times the amount of force? That's how we do torque. When we think about angular momentum, think about, all right, what's the perpendicular distance from the axis to the direction of the linear momentum? And then you can figure out what that particle's angular momentum is pretty quickly. Okay. One last thing. So most of what you're going to talk about in AP with regards to angular momentum deals with rigid objects. Okay. So when you have an object that's a rigid object that's spinning, we can write its angular momentum this way. Rather than using the RMV sine of the angle, we can use this expression instead, because what it does is it takes into account the position of every single particle that makes up the rigid object, and it multiplies it by its velocity. Well, its velocity is going to be, basically omega times r. So when you combine that all together, you're going to end up with this simple expression. Now, take a look at that. It looks very much similar to the linear momentum expression. All right, L is angular momentum. P is linear momentum. I is rotational inertia. M is mass, but think about what mass measures. It measures the inertia of an object. Omega is the angular speed. It's how fast something's rotating. V is the linear speed. It's how fast it's moving in a straight line. All right, so in very much a similar way, we can use this to calculate angular momentum, just like we use this to calculate linear momentum. Okay, we'll spend some time talking about calculations and stuff, but the two big ideas that are really going to be hit the rest of this week are going to be this. We can write the total torque as being the rate of change of angular momentum. So if something changes its angular momentum, it's because there's a torque acting on it. And if there is no torque, net torque acting on an object, then that means the angular momentum doesn't change. This is the whole thing you saw with the ice skater video. If you think back, the figure skater, we're going to talk a lot about this idea. This is a fundamental law of physics. This is the law of conservation of angular momentum. So we're going to get into this in quite more detail in the next few days, but this is just kind of an introduction to it. Okay, one last item. This is from the textbook. It says, what's the angular momentum of a figure skater spinning with arms in at 3.5 revolutions per second, assuming her body to be a cylinder of mass 55 kilograms and radius 15 centimeters. Okay, so basically they're saying if the skater's got her arms in and she's spinning around like this, that her body approximates the shape of a cylinder. With her arms out, obviously that would be different. But with her arms in, it's approximately a cylinder. So we're going to go with that as an approximation. Okay, so we're going to treat her as a rigid object. The angular momentum of a rigid object is I times omega. Okay, if we're treating her like a rigid object, a solid cylinder, it's going to be 1/2 her mass, which is 55 kilograms, times the radius, which is 0.15 meters, and we'll square that. And then the omega is in revolutions per second. We need to get that in radians. So 3.5 revolutions per second is going to be 7 pi radians per second. So 7 times pi is about 22. I should have known that. 22 radians per second. And we can get that the angular momentum is 0.5 times 55 times 0.15 squared times 22. I'm getting about 13.6. And the units, kilogram meters squared per second. Okay, so I want you to take your time and kind of go through these examples and what we talked about here. It's not my expectation that you're going to walk away from this and totally have an understanding of physically what angular momentum is. It's definitely a pretty abstract concept. Once we start getting into talking about conservation of angular momentum, you'll start to see why it's useful. But kind of understanding what it is at first is not something that's really easy to do. So we'll get into that some more. If you have questions or not sure about something, just shoot me a message in the comments and we'll take it from there. All right, take care, guys.